Adding polynomials. Objective of this lesson to add polynomials. Before we start adding polynomials, we need to take into consideration two area formulas. And the first area formula we need to know is the area of a square, which is s squared, and the area of a rectangle, which is length times width. Okay, these two area formulas become the foundation of algebra tiles. Algebra tiles make us model adding and subtracting polynomials. Okay, but let's add polynomials first. Let's represent polynomials with algebra tiles. You can use the concept of an area model to model monomials. A model of a monomial can be made using tiles drawings like the one shown below, and these are the tile drawings. Okay, this is unit tile because you have the dimensions of this square 1 by 1, which is a 1 by 1 square, and that's the reason why the area of a square becomes important. This is a unit tile simply because the area of this square is 1 unit. Okay, the next model we're going to talk about, this is the x tile, the area of an x. Why is that? Because you have the dimensions of this tile, the length is x and the width is 1. Multiply those two, you end up with an area of x, and that's the reason why it's called your x tile. Okay, the third model we're going to talk about is the x squared tile. Why is this x squared? Because it forms a square and each side has a measure of x, and we know from here that the area of a square is s squared. So here we simply multiply x times x, we come up with x squared. So this is an x squared tile. And we get the opposite of these three models. Okay, the opposites of these three models, the unit tile is -1. Okay, the x tile is -x, and the x squared tile is -x squared. Okay, they're all colored red to indicate that they are negative tiles. Okay, now how do we use these models? Okay, let's use these models to create a polynomial. Let's use these tiles to model a polynomial. Let's say, for example, you have this model. Okay, if you notice, there are two x squared tiles, three negative x tiles, and four unit tiles, four positive unit tiles. Okay, so you know for a fact that if you have two x squared tiles, that is 2x squared, and you have three negative x tiles, that is negative 3x, and four unit tiles, that is positive 4. Simply combine all of them together, you end up with 2x squared minus 3x plus 4. Okay, so your algebra tiles basically model your polynomial. In this case, 2x squared minus 3x plus 4 is what is being modeled in your algebra tiles right here. Okay, how do we use this? First, let's talk about some definitions, and then we'll discuss how we use algebra tiles to add polynomials. Okay, let's talk about what a coefficient is. The numerical part of a monomial is called the coefficient. Okay, for example, 5x squared. Okay, the coefficient is 5. So the coefficient of 5x squared is 5, the numerical part of our monomial. Okay, another probably good example would be, let's say if I have 6x squared. Okay, talk about, we bring this up, and let's say I have the polynomial. Okay, let me erase that thing. Let's say I have the polynomial 7y squared. Okay, the coefficient of 7y squared is simply 7, because that is the numerical part. That is the numerical part of the monomial, 7x squared. Okay? So this becomes your coefficient. Another good example would probably be 3. Let's say I have 3x z y to the second power. Okay? Or let's make y second there in order. Y squared z. The coefficient of this monomial would be 3. Okay? So that's what a coefficient means. It is the numerical part of the monomial. Okay? When monomials are the same or differ only by their coefficients, they are called like terms. Okay? For example, 2x and 7x, negative 5x squared y, and 9x squared y are like terms. Why are they called like terms? Because look at this carefully. Their variables are the same together with their exponents. So variables and exponents are the same, x squared y, and they only differ by their coefficients. So it's 2x and 7x are like terms because they only differ by their coefficients. Negative 5x squared y and 9x squared y are like terms because they only differ by their coefficients. Okay, so those are called like terms. 6a negative 5b, 7a cubed b squared, 7a squared b are unlike terms. Okay, simply because look at their variables. 6a is a variable of a, negative 5b is a variable of b. They are unlike terms. Okay, in the same manner, even though 7a cubed b squared, 7a squared b have a and b as variables, their their exponents are not the same. This has 3, this has 2, okay, and look at b. b has 2, and this one has only 1. Okay, so these are not like terms, they are called unlike terms. Okay, like terms are represented by tiles that are the same shape and size. Okay, so when you talk about like terms, they're represented by tiles that are the same shape and size. So another definition, a zero pair is formed by pairing one tile with its opposite. Okay, meaning if you have a negative 1 tile and a unit tile, this is what we call a zero pair because a negative 1 plus 1 equals 0. Okay, that's why it's called a zero pair. Okay, the opposite of another tile. You can remove or add zero pairs without changing the value of the polynomial. So we are now given 4 guidelines. The first one is defining what a coefficient is, okay, which is a numerical part of the monomial. The second guideline is knowing what like terms and unlike terms are. Okay. Third guideline is knowing what zero pairs are, and finally, when you remove zero pairs, you will not change the value of the polynomial. Okay. Now, how do we use these to be able to add polynomials? Let's find out. We have the model below, which represents 2x squared plus 2x minus 4 plus x squared plus 3x plus 6. Why is it 2x squared? Because there are 2x squared tiles, 2x tiles minus 4 because there are 4 negative 1 tiles. Okay? And it goes with the same 1x squared tile, 3x plus 6. Okay. Now look at this very carefully because once we start adding this, okay, it's we can combine our algebra tiles and have something like this. To add polynomials, combine like terms and remove all zero pairs. So in this case, how did we define our like terms? Okay, we define our like terms as terms in the tiles, okay, that are the same. Okay, so in this case, we combine all the x squared tiles, we combine all the x tiles, okay, the unit tiles, and the -1 tiles. Now, if you notice, these the 4 negative ones and the 4 positive ones have been circled because they are 0 pairs, which means we can actually take this away and not change the value of our, okay, polynomial. Okay, and if we count the number of x squared tiles, okay, and we add them up, we have 3x squared, and we have 5x tiles, and what remains is 2 unit tiles. So 2x squared plus 2x minus 4 plus x squared plus 3x plus 6 is equal to 3x squared plus 5x plus 2. And that's how you use algebra tiles to be able to add those two polynomials. Okay? Now, okay. Now, how do we use algebra tiles to be able to add these two polynomials? X squared plus 4x plus 2 plus 7x squared plus minus 2x plus 3. Okay? Let's use algebra tiles to be able to add these two. Let's first consider x squared plus 4x plus 2. That means 1x squared tile. Okay? And 4x tiles. Okay? And then plus 2 unit tiles. Let me put them on top of each other. Okay? And then you have 7x squared. So 7 of these babies. 1, 3, 4, 5, 6, 7. Okay? And then negative 2x, so that means 2 of the negative x tiles and 3 unit tiles. Okay? So let's consider that. That means let's add like terms. In algebra tiles, like terms mean those tiles that are the same. So in this case, we'll add all the x squared tiles. And if you notice, we add all the x squared tiles, we end up with 7x squared. But let's look at the x tile and the negative x tiles. If you notice, if I get 2 of these, okay, and if I get these two, okay, what happens is this becomes, okay, a 0 pair. So we can actually take this out. Okay, so what do we have left? We now have, okay, going back here, let me put up my screen. Okay, not that one. So you have 7 or 8x squared tiles. Okay, so you have 8x squared tiles left, and 2x tiles left, and 5 unit tiles left. So the sum of these two polynomials is 8x squared plus 2x plus 5. Okay, that's how you use algebra tiles to be able to model that the sum of those two polynomials. Okay, now it would be very impractical to use algebra tiles every single time we add polynomials. So what can we do? We can use the principles and properties that we learned in the past about integers and rational numbers to add polynomials. Now how do we do this? Let's say you have 5x plus 7 plus 3x plus 3. Okay, these are two polynomials. that we want to add. So what do? Method 1, we add them vertically. Okay. Notice that the terms are aligned and added. 5x is lined up with 3x. 7 is lined up with 3. Basically, we're lining up like terms. Then going back to our definition of like terms, what are like terms again? Like terms are when, okay, then you have two expressions, okay, who have the same two expressions with the same variables and exponents, and they only differ by their coefficients. So in this case, you have x and x. They have the same variable and the same exponent 1. They only differ by the coefficients. That means we can add them. Okay. Now I have 5 plus 3 equals 8. And since 7 and 3 are constants, okay, simply add 7 plus 3, end up with 10. You have now 8x plus 10. Now, why can't we simplify this further? We cannot simplify this further because 8x and 10 are not like terms. So, if they're not like terms, you cannot add them. So this is the simplest form of 8x plus 10. Okay? The second method is that we add them horizontally. And if you notice, when we add them horizontally, the first property that we can apply is the associative and commutative properties of addition. Why associative? Because we are grouping the terms 5x and 3x and 7 plus 3. Why commutative? Because we are moving them as we group them. So we moved the 3 in place of 7, okay, and the 7, we basically switched the 3 and the 7, okay, and we group them. That's why it's called associative and commutative properties of addition. And what do you notice about 5x and 3x? Okay, 5x and 3x, we can use the distributive property so that it becomes 5 plus 3 multiplied by x plus 7 plus 3. Okay, we simplify further. 5 plus 3 is 8. Okay, and 7 plus 3 is 10. Same answer. Okay, so those are two methods that you can try to be able to solve those polynomials, vertically and horizontally. Okay, let's look at another example. You have 3x squared plus x plus 2 plus x squared plus 2x plus 4. Okay, again, copy the problem down, and then let's see how this is done. You have 3x plus x squared, x plus 2x, 2 plus 4. What property is this? Okay, the property is, again, associative and commutative properties. We are just basically getting our like terms and putting them next to each other, and so that we can add them. Okay, and we know that 3x squared plus x squared becomes 4x squared. X plus 2x is 3x, and 2 plus 4 equals 6. So the sum of that polynomial plus another, and that polynomial is 4x squared plus 3x plus 6. Okay, how about this one? 2x squared plus 5xy plus 7y plus 4x squared minus 3y squared. Okay, look at this. We add them horizontally. And what do you notice? Okay, we lined up our like terms. 2x squared has been lined up with 4x squared. 7y squared has been lined up with negative 3y squared. And we simply add them horizontally. This is x squared, 6x squared. Simply bring down 5xy, and then 7 minus 3 gives you positive 4y squared. So the sum is 6x squared plus 5xy plus 4y. Another way you can do this is this method. Okay, if you have the same example, okay, make this bigger a little bit, okay, and let's use the same example, 2x squared plus 5xy, okay, plus 7y squared, and I'm going to add it to 4x squared minus 3y squared. Since you're adding polynomials, you can simply take away the parentheses and add them directly. So I'm going to tell you later on why that is possible. So you can take out the parentheses. Now you have 2x squared plus 5xy plus 7y squared plus 4x squared minus 3y squared. And what I like to do is I like to underline my like terms. 2x, okay, is alike with 4x squared. If you notice, I am also underlining the sign or the operation before the number that tells me the sign of the number. Okay, remember what we talked about in the past. In terms of addition and subtraction, the operation before the number is the sign of the number. Okay? Okay? Look at 5xy. I'll double underline it now because now this is a different term. Okay? Has no like term, so we leave that alone. And then we now have 7y squared. Underline it 3 times. Okay? Is alike with negative 3y squared. Okay? And then add, okay, the terms that you underlined. You have 2x squared and 4x squared has the same number of lines. So 2x squared plus 4x squared is 6x squared. 5x squared doesn't have a like term, so I simply get 5x squared, or sorry, 5xy. And then I get positive 7y squared minus 3y squared will give me positive 4y squared. So there's another way of adding your polynomials. Okay? Let's look at this example. It should be the last one, I think. Or I think I have one more here. Yep, I do. Okay, let's do this first. Polynomials are often used to represent measures of geometric figures. The lengths of the sides of golden rectangles is what we call a special ratio. The rectangle at the right shows the lengths of the sides of a general golden rectangle. So if you have a general golden rectangle, okay, the width is x and the length is 1.618x. Okay. We want to find the perimeter of the rectangle, of our golden rectangle. Okay. Now, why is it called a golden rectangle? Because golden rectangles are a special type of ratio that ensures a strong structure and at the same time very pleasing to the eyes. Okay, so that's a lesson for another day. Let's do this first. Find the perimeter of the rectangle, 1.618x, which is our length, and the width, which is x. Okay, now what is being assumed in this problem? It is being assumed that we know what perimeter is. Perimeter is simply the sum of all the sides. So we simply add all the sides, x plus x, 1.618x plus 1.618x. And this is what you come up with. Adding all the sides, you end up with 1 plus 1.618 plus 1 plus 1.618. Okay, using the distributive property, put them in parentheses and multiply that by x. Since they are all like terms, we can add all of them. You end up with 5.236x. Now, you might ask, where did 1 come from? Okay, remember, okay, when you talk about the variable x, okay, it is always known that there is an invisible 1 before the x. So the coefficient of your x here is 1. Okay? They just don't write it. Or we just don't write the 1 before the x. If you don't see a number before the variable, it is always a 1. Okay? So, we found the perimeter to be 5.236x. Let's answer B. Find the length, the width, and the perimeter of the rectangle if x is equal to 5.2. So this is simply substitute and simplify. We will evaluate our perimeter. Okay, we make x equal to 5.2. Okay, if x is equal to 5.2, then the width is 5.2 units and the length is 1.618 times 5.2. Makes sense? And the perimeter is 5.236 times 5.2. Okay, because of what we have here. Which brings us To the substitution of the values, the length is 8.4135, okay? And the perimeter is 27.2272. And that's how you use adding polynomials to be able to solve word problems such as this one. And let's see how do we solve this in this last example. In this last example, we're being asked to find the perimeter of the rectangle shown at the right. Oops. I just showed you the answer, 6x plus 24 units. Why is it 6x plus 24 units? Let's find out. If I have that rectangle, 2x plus 7, okay, and you have x plus 5, we know that in perimeter formula, okay, perimeter of any rectangle is equal to 2 times the length plus the width of the rectangle. In our case, our length is equal to 2x plus 7, and our width is equal to x plus 5. Substitute the values to our formula. Okay, we now have perimeter is equal to 2 times 2x plus 7 plus x plus 5. Okay, now look at the 2x plus 7 and x plus 5. We have like terms in, okay, 2x and x are like terms, 7 and 5 are like terms. But before we add them, let's take out the parentheses. So p equals 2 times 2x plus 7 plus x plus 5. Okay? And these are our like terms. Right here, right there, there, right there. Again, if you notice, I am also underlining the operation before the number because that tells me the sign of that particular number. So p equals 2 times 2x plus x equals 3x. 7 plus 5 equals 12. Using the distributive property, this becomes p equals 6x plus 24. So the perimeter of this particular rectangle, okay, has the expression 6x plus 24 units. Okay, same thing we have here. Okay, so that's how you use like terms and unlike terms to be able to add polynomials. I think that's the end of the lesson. So in your notebook, write a summary of what you've learned in this lesson and post it on Google Forms. And at the same time, write a question you may want to ask in class. Thank you.